Okay, good afternoon. Welcome back, everybody, and thank you for joining me for the last session of the day. I hope you've enjoyed the day as much as I have, and you've learnt as much as I have, because I know I've certainly picked a few things up as we've gone on, especially in the last session with Frankie and Pete there. So, we of course save the best till last, and that leaves us with what is flexible manufacturing and how can it help? So Frankie and I are going to try and clear up some myths surrounding flexible manufacturing, so hybrid machines, 3D printing, and just generally out of reach expensive equipment. So before we get started, anyone joining today that hasn't met me, my name is Curtis and I've been with Man & Machine for a little under 3 years now. I come from a customer service background and I've really enjoyed transferring those skills over to help my customers realise their maximum return on their investment. Now, what's that about? It's about making better products, reducing errors and increasing efficiency ultimately. Frankie will introduce himself in a moment, and if you haven't met Frankie yet, there'll be a 2-minute video to grab a coffee at the end of this. I'll give you plenty of warning. Between me and you, you're going to need it. Let's get going. So what I wanted to do, as you've probably seen with the theme, is kick the session off with a quick poll. I wanted to understand what you thought flexible manufacturing meant to you. So does it mean 3D printing, hybrid machines? Does it mean robots or efficient manufacturing or even generative design? So I'll give you 30 seconds or so to get your answers in, and Simon or Rob will fire the link into the chat now if they haven't already done that for me. Okay, so I think we've got most of the responses in now, and we're just putting those together for you. So, yep, we're good. So, if we look at what you guys are thinking, then actually it looks like nearly 80% of you think that it's robots or additive manufacturing, some kind of hybrid machine, I suppose. Surprisingly to me anyway, less than 5% of you believe it to be generative design. But let's take a look at the industry and the journey of manufacturing and where it's been. We're all familiar with the traditional manufacturing process, right? So as manufacturing businesses, we've always been tasked with designing products, mainly with fabrication in mind or subtractive manufacturing through CNC machines. Designers would throw their drawings over the wall, sometimes literally in that sense, and then the business had to determine whether that was even manufacturable when it got into production. They would have to interpret those drawings, maybe make small changes. This all raised questions and uncertainty at the time. Can it be made? At what cost, and how quickly ultimately? Often those questions in the past have been answered with experience and knowledge, right? Unfortunately, a lot of those people are coming to retirement age. Other than apprentices, which there isn't many of these days, it's been really difficult to replace those machinists and those people with that experience within business. In fact, 40% of people struggle to replace their CNC machinist. So what's next? We know how quickly the world is changing around us. We know that our customers are expecting more of us and that products are getting more complex, right? The industry has always found it hard to remain competitive and profitable at the same time. And with the potential loss of some of that experience, who knows what's going to happen to those resources and material costs in the future. Now more than ever, it's important to really take control of our manufacturing process. Truth is, British manufacturing has always done a fantastic job of staying current. We're an incredibly proud bunch when it comes to our manufacturing. UK made products, right? That badge that says made in Britain really means something to us. The industry has always embraced new technology, and in recent years we've seen wonderfully creative and innovation to bring those new products to market. In fact, we see well over 30,000 new innovative products every year. Really, this is all because of flexible manufacturing. It simply means that manufacturing that can adapt, manufacturing that can keep up with the demands of our customers. We mentioned before that those expectations are changing. And I'm sure we've all made a purchase recently where we've had higher expectations than the last time round. A new sofa, a new wardrobe from that new Swedish company that we all love so much. It's all completely customizable. And their manufacturing processes have to be able to cope with that demand. So what are the industry leaders doing, and what does flexible manufacturing look like moving forwards? We're all familiar with the automotive industry, that 24/7, 365 production line. Of course, this is going to be overkill for most manufacturers, but the message is to make sure that you are able to adapt. Post-processors for CAM, designers that understand what's manufacturable and what isn't. We already know that people are having to take on more responsibility within their roles. 3D printing for prototypes to save on material and time. Generative design perhaps, or even automated production driven by configurators. Of course, we're not all living in a world where we're in a 24-hour robotic factory, and most of us wouldn't want to. But the idea of being as efficient and cost-effective with your manufacturing process as possible and taking back that control still applies, maximising the return on your investment. With all that being said, I'll hand you over to Frankie, and that 2-minute video is coming up for you to grab another coffee that I warned you about.
Thank you, Curtis. How cool is that motorcycle? The swing arm with the organic generative design, so futuristic. I love it. That would take some advanced manufacturing techniques. So what we've been exploring all day without maybe even realizing it is Autodesk's approach, the digital prototyping. So the idea is that we can use software like Revit and Inventor to create things like the geometry and the materials and all the metadata that goes into the designs. We've optimized the design a little bit. We've optimized the design and we've verified that it works using Nastran. So basically we prescribed the load cases and we made some adjustments to the material, and now we're happy with the design as it is. So the final piece of the puzzle is manufacturing the thing. You could have the best design in the world, but if it's not manufacturable, then it's not much use. So back in the old days, we used to make everything by hand, or then manual machining came along and we could do things by manual machining. Then NC codes came in and people could type in some coordinates into the machines and type in some G code, and they could manually program machines on the fly. But the cutting edge is really having the computer take care of the machining toolpaths for us. What we're going to explore today is Inventor's CAM tool. So Inventor's CAM tool allows us to take a part or an assembly of parts and define the machining toolpaths that are required in order to cut it out on a CNC machine. And that's what we're going to be having a look at today. So we have the awning from the previous exercise. We're happy with the design. We know that it works. We're going to go into the parts and we're going to define the toolpaths to cut it out on a CNC machine. So I'll choose this arm here and we're going to pick on this arm. So let's look at the design. It's got a few features about it. We'll have a look at it before we continue. So if we measure it, we can tell that it is 15 millimeters thick, that it's got pockets that are, let's see, measure that, 3 millimeters thick. The pockets have radii on them, 16 millimeters in diameter. And we've also got the pin joints here. So the pin holes are 13.5 millimeters in diameter. And we also have these threaded holes for the fastener. 6.647, so I take it that's an M8 tap hole. That we're going to need for the slats that go on top. So how do we machine all of this? You could arguably, make a drawing from it and have a manual machinist, cut it out on a machine or manually program the NC. But we're going to have a look at how we can make those toolpaths within Inventor CAM. So as with Nastran, the Inventor CAM tool is actually incorporated into Inventor, and so you don't actually have to leave the Inventor environment to use it. So let's go ahead, we'll come to the CAM tab. And like generally speaking with all the Inventor tools, you work from left to right. We're going to start off by defining what's called the stock. So this is the bit of metal that you're cutting the part out of. So we'll go ahead and start that up. And say set up. And from the get-go, we get asked, what is the operation type? Are we doing milling, or are we doing turning, or are we doing maybe additive or cutting? In this case, we're going to be using a milling machine to cut this out. It might be a bit expensive given how large it is, but nonetheless, these are the kind of items that get cut out on CNC machines all the time. Maybe at the end we'll explore some of the turning operations, but for now we'll just have a look at milling. So in modeling, it tends that that Y is up, but in machining, it tends that Z is up. So we're going to change the work coordinate system. We'll come here and define Z to be upwards. We also get to define what the x-axis is. So we can pick x-axis, and now we can pick a straight edge representative of the x-axis. Beautiful. Lastly, we've got the stock point. So what is the 0, point on your machine? This really depends on how you set up your machine. But for this exercise, what we're going to do is show the stock point in the lower left-hand corner. So we'll come to stock point, and here we can zoom in on the corner and say it there. That point, that's our 0. Beautiful. All right. Next, we have to define the stock. So, what exactly is the material that we're cutting it out of? Not material properties, but the size of it. You can define the stock in a number of ways. You can define it from an existing solid. So say, for example, you've already done machining operations, and that can be the input for the next one. Or you could say from a fixed size cylinder or a fixed size rectangle. In this exercise, what we're going to do is show a relative size box. So we're going to say, okay, let's go ahead and add in 2 millimeters of material on all the sides. We'll put 2 millimeters of material on the top, and on the bottom we'll have 3 millimeters of material. In reality, in fact, it might be a bit bigger than that, so we might say, let's go ahead and put 12 millimeters of material. 13 millimeters for good stuff. So here we can see the stock. It's 2,079 millimeters wide, 104 millimeters tall, 30 millimeters wide. So we might say, maybe that's a non-standard value. We might go ahead and change the side offset to 2.5, and there we go. We've got 2080 by 105 by 30 millimeters stock. Looking good. All right, let's go ahead and click OK. So in yellow, what we can see is the stock from which we are cutting the material. We have to leave some material on the bottom because you need to hold it in a vise. Excellent. So the way that this works is that we define the cutting operations, operation by operation and tool by tool. So generally speaking, the first operation that you do in this scenario would be a facing operation. So you start off with a big face mill, 50 millimeter cutter, and have it run along the surface back and forward to make a nice surface finish. So here we can pick the facing operation. Lovely. So one of the best parts about all the Autodesk products is the homogeneity of all of their tools. So what you'll notice is that with each of these machining operations, we have the same 5 tabs. We've got tool, geometry, heights, passes, and linking. And each one of them serves a repetition function. So tool, we choose the tool. Geometry, it picks what exactly we're cutting. Heights are the depths that we're cutting to. Passes give flavor to the cutting operation. So things like pass extensions or step downs and whatnot. And linking affects how it starts and stops the operation, how long the tool's allowed to stay down. So we might change the tool, and we'll find from the very extensive default tool library in Inventor CAM. We can find any tool that we want. So we've got any drills, mills, turning tools, flat mills. What I want to do is find a nice big face mill. So this is literally made for just cutting off the top layer of a component. So we'll choose this 50mm facing tool. At any time you can edit these tools so that they match the tools in your CNC machines, and we'll go into that a little bit later. Let's go ahead and click select, and now we've got the 50mm facing tool. The geometry for the facing operation by default is just the entire component, so we'll leave that as is. Under the heights, that does it automatically as well. For the passes tab, here we can affect the pass direction. So what direction is the face tool running? Is it running at 90 degrees or is it running at 0 degrees? We want it to run at 0 degrees, so we'll leave it as default. As for the pass extensions, by default, what the facing tool is going to do is come to the end and then immediately turn around, but that can leave some tool marks on there. So we're going to add in something called a pass extension, which means that the tool will go beyond the component and then turn around. Very good, very professional. Let's do it. Pass extension 25 now. And stock offset adds a little bit of imaginary meat to the side of the stock so that the tooling will capture that as well. We'll say 10mm stock offset. We're looking pretty good. We're looking pretty good. If we go to the linking tab, we're happy with that. If we go to the tool tab, here we can see the feeds and speeds that are used in this operation. So these defaults can be set according to tools and according to operations, and really are affected by what material you're cutting, what precision you're cutting to, what tools you have, etc. So these are just the defaults that were programmed with the tool. But if you want to make it faster or slower, you can say change the feed rate per tooth, or change the spindle speed or the surface speed. But this will just leave it as default. Let's go ahead and click OK. And now we get a vision. We get to see a preview of the operation that's happening. So the tool is going to come down here, start cutting, come across the tool, and all the way back, extend beyond the surface, and then turn around and go back and forward until it finishes. Now, from my experience, it always pays to simulate it. Let's see what it actually looks like in operation. We'll say simulate. I'll turn off the toolpath and turn on the stock, and maybe make the color a bit more like the real color. Okay. Make it. There we go. Okay. So what we can do here is hit play, and now we get a preview of the tool coming down and cutting across the material. So we get a complete preview of the operation. Looking good, looking good. Okay. So I might just disable shadows because that can slow it down sometimes. There we go. Lovely. So what we can see is that it's cut off the top layer, that was the extra bit on the top. Now, what we'll probably want to do next is a contour, because we've got some additional meat on the side here. It's not actually meat. Don't cut meat this way yet. It's definitely metal. But we want to cut the metal away from the perimeter of the component. So what we're going to do next is coming in with an adaptive clearing operation that we're going to do on the outside of the part. So here we'll come along to the CAM tab again. And now we can do this in a couple of ways. You can have concentric contours, but we'll do the adaptive clearing. So adaptive clearing of tricordial milling is basically a very, very rapid way of getting rid of a lot of material. Now, it tends that the surface finish for this kind of operation tends to be pretty bad, but it's very, very good at getting rid of a lot of material very quickly. So if you've got a cycle time of maybe 2.5 hours with a regular pocketing operation, something slow and methodical, it might only be 2 hours if you use adaptive clearing for getting rid of this. It's a roughing strategy. Well, have a look at it. So we'll say adaptive clearing. And this time we're going to change the tool. We're going to use a very big flat mill. So we'll find the biggest flat mill we've got, 25 mil. That will do. Great. And next, what we're going to define is what are we going to adaptively clear? We could choose one of these pockets and clear that out, but we have to get the perimeter first. So we're going to pick the outside of the component. And highlighted in blue, if you can see there, are all the bits of material that it's attacking. So this is all the extra stock. Now by default, it's just going to cut to that level, but we really want it to cut to the ground. So let's go ahead and we're going to say the bottom height of this operation is the model bottom. And then say we wanted to punch through the bottom by 2 mil, just to be sure. So we might say -2. Next, under the passes tab, here we can influence how it's doing the cutting operation. I'm going to leave it mostly by default, but I will point out 2 things. So here we can define multiple depths. So this is a high strength steel, so it may be that it can't cut the full amount of material all the time, all the way. So you might prescribe that it can go down only say 8 millimeters at a time, as opposed to the full 15 millimeters all at once. So we're going to tick on multiple depths and say that the maximum roughing step down allowable is in fact 8 millimeters, or let's make it 10 millimeters just because the stock is quite large. Okay. Next, we can say the stock to leave. So because it's a roughing operation, the surface finish for this kind of operation tends to be a bit terrible. So what we're going to do is leave some stock on the sides. However, for the axial stock to leave, we're going to set that to 0. So to reiterate, what that's going to do is leave 0.5 millimeter of metal all the way around the perimeter of this component. All right, I'll go to linking, make sure everything's in order, stay down the most. Wonderful. All right, let's go ahead and try it out. So we'll say okay. And what we're going to see is a lot less elegant toolpaths than what we just witnessed, but very, very effective. So what you'll see in the spaghetti is the tool coming down, and what it does is it follows the contour of the component, and it tries to keep a constant load on the tool. So whether you're cutting climb mill or conventional milling or both ways cutting, it will try and keep a constant load on the tool. We also prescribed a maximum step down of 10 millimeters, so it's actually cutting this in 2 separate levels. But let's have a look at what that looks like. So we'll come to setup, simulation, and we can go ahead, we can see the facing operation, we can speed it up. Looks good. And now it's going to come down with the adaptive clearing operation. So as you can see, it's trying to keep a constant load on the tool, and it's only going down a maximum of 10 millimeters at a time. So it'll clear out, clear out, clear out, clear out, clear out. There we go. And you might say, oh, what's this bit on the bottom? We only said go to the bottom of the model plus a little bit. If we were to show turn on part comparison, we can see the stock that remains to be cut, as well as the gray showing the material that's cut to level. So what we're going to do next is a contouring operation that's going to follow along the perimeter of this component and get a nice surface finish on there. So we'll say close. And next we'll come along to 2D contour. And this operation is very, very, very nice because it's easy to set up. We choose our contour and we choose the side which it's applying to using this arrow. And now for the heights, we might say, okay, we want to cut to the bottom of the model, -2. Oops, model bottom, -2. So it's going through the bottom. Next, the passes. If we want to do multiple circuits of it to make a different surface finish, we can do that here. But the only thing that I really want to touch on is a finishing overlap. So when it gets back to its starting point, it goes a little bit further just so that it gets rid of any slivers that are left there. As you can tell from all the dialogue, it's quite comprehensive in its options for these kind of operations. And for the linking, I'm just going to make sure that the tool can stay down. Lovely. We'll click OK. And now we should see very quickly generated a very simple operation where the tool comes down, it cuts all the way around the perimeter, and then it leaves where it's a little bit after where it starts. So simulating it again, we can hit play, fast forward through the whole thing. Adaptive clearing operation clearly gets rid of the material, and then we've got the contouring operation, which is doing a nice surface finish on the end there. And if we need to see, we can turn on show part comparison, and it will show the actual material versus the stuff that's yet to be cut in blue. You might notice that there's a bit of a coloration here. That's just because we've made it in an approximate way using the simulator tool. So what we're going to do next is come in with some tools, clear out these pockets and give them a nice finish. Come in with drills, drill these out, and tap the rest of the holes. So let's go ahead and say done. Ooh, for the contouring operation, I should have made sure that, yes, it didn't have any stuff. Good stuff, good stuff. Excellent. Okay, so next what we're going to do is come along with a 2D adaptive tool. So the same one that we used to clear out the outside, but this time we're going to choose a smaller tool. Now, when we measured the radii of those pockets last time, it was 16 millimeters in diameter. So we need a tool that's maybe a little bit smaller than 16 or 16 mil at the very limit. We'll come along here and say, let's choose a tool by type. And we're going to choose, rather than a flat mill, which would actually get the nice sharp corner, we're going to use a bullnose mill to leave a nice little fillet in the corner there. So let's have a look at what that will look like in practice. So we'll choose a 12mm tool. Here we go. Lovely. And now we can come along and choose what we're doing the adaptive clearing operation for. So we can pick multiple pockets. 1, 2, 3, 4. Fantastic, excellent, awesome, good. Okay. For the heights, it's cutting to the height of those contours. For the passes, here we can choose if we're cutting down multiple levels. Now these pockets are only 3 mils, so it's nothing. But as before, it's not a finishing operation. So we're going to leave some stock on the sides, both radially and axially, so stock on the bottom too. And for this time, we are going to use both ways cutting. So ordinarily when we're doing a clearing operation, it's making a cut, then retreating, then making another cut, then retreating, then making another cut, and retreating. But if your machine and tools are strong enough, it's possible to cut with both sides in a back and forth fashion. It's faster, it's rougher, might lead to more tool wear, but maybe the benefits outweigh the consequences, because it's you'll see it's very pretty. So good, stay down level, maybe we'll set it to the most, and now click OK. And let's have a look at the machining toolpaths. So what it's doing here, as you can see, is it starts off with a helixing operation. So it's coming down, vroom, 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 vroom. And then it's basically just doing a spiral pattern. In fact, I don't even think it does the both ways cutting here, but that's okay. We'll get to see what it looks like. It's very pretty. We can hit simulate again, and we don't have to go through it all again. We can skip on the timeline here, and it will skip to the portion that we're up to. And let's have a look. So it'll start coming down. Yes, it's a nice pocket, very good. And it will rough out that pocket there. Maybe I could make that more efficient by choosing the entry point, but for the sake of demonstration, we'll continue. If we turn on show part comparison, we told it to leave 0.5mm stock on there, so we can see that there. Here we go. So let's go ahead and add in a finishing operation. So we're going to use a 2D pocketing tool. So we'll choose 2D pocket, and this time we're going to pick that one, that one, that one, and that one. Fantastic. And this time I really want it to get that sharp corner. So I'm going to change the tool to a 10mm flat. Wonderful. Next, for the heights, by default, it's trying to start from the top of the stock. Now, if we're only making so many of these, it doesn't really matter, but if we're making lots, then the cycle time really matters. So you might say, rather than starting the spiraling down from the top of the stock, let's go ahead and start it from the top of the model. And then it was 3mm deep, we've left on 0.5, so we might say top of the model -2. And there we go. We've got a nice, neat pocketing operation for each one of these pockets. Fantastic. If you want, you can just simulate that one strategy rather than doing the whole thing by clicking simulate. Turn off part comparison, turn off the stock, and here we can see what it's actually going to be doing. So there it's doing the pocketing operation, a nice spiral. Beautiful. Great. Okay. Next we'll come along, so that's finished the pockets, we're happy with that. Next we'll have to come along with the drill and cut out those pinholes that are being used to fasten this thing. So let's go ahead, we'll choose we could bore it out if we wanted to, but we've got a big enough drill for this. We've got a hole that's 13.5mm in diameter exactly. We'll choose a drilling operation. And here we could use an end mill, but let's go ahead and find a drill. We'll pick from here, drill, and we'll find something that's 13.5mm. There it is. Perfect. Select cool. Now, in this case, I'm going to pick both of the holes. Lovely. Now, we've got a problem. When we look at it from the side, it's going to the bottom of the hole, but it's just touching the tip of the drill onto the bottom of the hole there. So what we want to do is really tell it to punch way to the bottom. So under the heights tab, we can find hole bottom, and say drill tip through the bottom. Yeah. Let's do it. And let's have a breakthrough depth of 2 millimeters. In case we've got any of those slivers, we want to, boom, cut them right through. So, good. Now, if it's a simple hole, you might just drill, go out, in and out like that. But it's also possible to do chip breaking. So say, for example, you've got a long hole or, galling material or something like that. You might want to adjust the approach of your drilling rather than just going into the hole and coming out. You might say, go in a little bit and then come out, then go in a little bit more, then come out, then go in a little bit more, then come out. And then when you get to the end, dwell a little bit. So many, many different nuances with drilling. Who would have thought? Here we can come along and we can change the cycle type from a rapid out, regular time that we're drilling to chip breaking partial retract. So what that means is that it will peck in a certain distance, and then it will retract, and then it will peck in a little bit more, then retract, then peck in a little bit more, then retract. We can so the pecking distance here we might say is 5 millimeters. So it'll go in 5, then retract 5 mil, then retract. We can also tell it to dwell at the end. So when it finally gets to its goal, maybe hang there for about half a second just to get any excess out. So we might say dwell before retract, and set the dwelling period to 0.5 seconds. As you can probably see from the common theme, there are lots of settings for even basic operations like drilling. But at the moment we're doing it in a very manual way. Okay, so there we've got the drilling operation sorted out. And we can quickly have a look at what that looks like, although it'll be as you'd expect it to be. What a riveting story. Excellent, great. All right, now we have a bit of a challenge. So far, all our operations have been down from the top like this. So, the tools have come down from the top. This is 3-axis, so almost 2.5 axis machining. What we're going to do now is assume that we've got a 3+2 machine. That is to say that the machine can grab the model, grab the stock, and put it on another angle, and we can approach using another angle for the tool. And we're going to use this for doing the drilling operation for these side components here. So as we can see, we've got holes for M8, and if we measure it, we can see that the internal diameter is 6.4 millimeters. So these are threaded holes, partially threaded I should say, and they're going to require 2 operations. So the first operation is just going to be a drill that will get rid of the bulk of the material. We might start off with say a 6 millimeter drill. And get all of the holes to depth. And then we're going to come in with a tapping tool using the drilling operation in here as well. And we're going to tap that thread as well. So let's have a look. We'll come along here, and this time we're going to choose the drill. And we're going to make a slight change. Obviously we have to pick the tool first. Let's go ahead and choose a drill, 6 millimeter. Oops, 6 millimeter drill. Perfect. And now what we're going to do is we're going to pick one of the holes. And you might say, hey, what gives? Last time we got a preview of the toolpath that it intended to make. Why isn't it doing that? That's because unless you tell it to, it's going to assume that you're using just a 2.5 axis machine. However, if we were to come along here and say change the tool orientation, we can now specify that to be the Z direction and this to be the X direction, which is fantastic. So basically, it's going to come in from the side now. In reality, what the machine would do is it would flip the part like that, tilt it a little bit, and then you'll come in with the drill from the top. But that's all handled by the post-processor, which we'll talk about after. So we've chosen one drill, and being profoundly lazy, we don't want to select each one of these holes. That's crazy. So what we're going to do is just say pick all the holes of the same diameter. Wonderful. And it goes through and it automatically adds the drilling operation to each one of these holes. Now, unlike our previous hole, we don't want this to punch through. We want it to punch to that level. Or maybe just put the drill tip through the bottom, but not go any further than that. Lovely. This time for the cycle, we'll do again chip breaking, partial retract with 0.5 seconds dwell. You can change these defaults if you want to. Go ahead and say OK. So it's going to be a little left field, literally. Have a look. We'll hit play on the simulation, and now it looks like the tool is coming in from the side there. Drill, 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 drill. Wonderful. So the last operation that we really need to hammer down the top features of this component are the threads. So we've got the holes in there, and they cut 6 millimeters, but it's actually an M8 hole. So we have to come in with an M8 tap and actually cut out that thread. So this is actually a very, very easy process. We'll come along to drill. And this time, we're going to change the drilling tool to a tapping tool. We'll say a right-hand tap, and we'll find an M8 tap. There we go. M8, so there we've got the 8 by 1.25 or the 8 by 1. So for this design, it's a 1.25 tap. Lovely. And as before, we're going to change the tool orientation so that Z is facing in that direction and X is facing in this direction. As I said before, in reality, your post-processor would grab these machining toolpaths and flip the stock up, and the tool would just come in from its usual angle. Great. All right, so next we'll come along and we can choose each of the holes. Oops, I overrode something I shouldn't have. Hole bottom, there we go. Yeah, there we go. So I'll pick the geometry, pick the holes that we're machining. That's it. And now we can say all the holes are the same diameter. So again, it'll go off and it will select each of the holes in this. And this is to add in the tap, the thread. So we'll say okay. And there we've got the complete operation. Fantastic. It's automatically done it for us. Okay, so I think that we've got all the toolpaths that we need to machine the top part of this. It might be worth doing a complete simulation just to make sure that the tool's not crashing, and we can even see how long it's going to take. As I mentioned, in each of these operations, we brought in the tool, and the tool brought in the default speeds and feeds for that operation. So say, for example, we've got a particularly fast tool that might be able to go, 8,000 millimeters a minute across the surface, or maybe we've got a slow tool which is only, 200 millimeters a minute. Depends on the tool and the material. But what we can do here is click simulate. And now we get the opportunity to see the entire operation. So we'll come along. Here we can tick on stop on collision, but the tool's not going to collide with anything. We were smart about it. Say plus, play. And now it's going through the whole operation. Cut, 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 cut. Looking good. Comes in, does the pocket clearing operation. And then it comes in with a finishing touch. And then it comes in and drills the side, and then it taps the side. Wonderful. Excellent. So now we can turn on show part comparison. And, oh no, we've made a mistake, I think. I think for our pocketing operation, we've accidentally left some meat on the bottom. Let's go ahead and correct that. So we'll sum to the pocketing operation, come to the passes, and here's the criminal. We'll turn off the stock to leave. So this is again for the roughing operations, but these pocketing operations are finishing operations. So we trust it. We trust it. Say okay. And now it's got the entire machining toolpath in there. Excellent. Simulate it again, super duper fast forward. Just skip to the end. Yep. And now we can compare, by turning on show part comparison, we can compare what we have to what we've cut out. Looking pretty good. I think the tapping was a bit aggressive. Wonderful. So how long? How long is this going to take? All that has to go off is an approximations from the feeds and speeds of the actual operations and the tools that we chose. So if we come to statistics here we can get an approximate machining time. So fantastic. This anticipates that with the machining time from the feeds and speeds, we got a total machining time of 4 hours, 46 minutes, and 25 seconds. A total machining distance of 82 meters. Now, you might show this to your machine shop operator and say, we can drive the tools faster, we can get it done faster. Maybe we can do faster roughing, but then go slower on the pocketing operations, for the surface finishes. A lot of things that can be tweaked to bring the cycle time down. But again, this is, for the machinists to decide, but if you want to tweak them, you can here. Now, the machinists mainly want two things as well. Firstly, they want a sheet that shows the setup. So what stock they're using, what tools are they using, what's the ID number of each of those tools so they can load up their CNC machine and approximate how long is each operation going to take. And that's what's called a setup sheet. So we've got that here. We can click setup sheet. And here we can choose to output in the form of an HTML file, a complete setup sheet. So it takes whatever image you've got open and takes that screenshot. So I should have done that better. But we've got the setup, so it shows what stock we're doing. So here we've got 2080 mil by 105 mil by 30 mil stock, and it's got the coordinate system for relative to the model, And here we've got a summary. So total number of operations, total number of tools. It's given the tools IDs, so T1, T2, T3, all the way to T7. Maximum feed rate and yada yada. It also gives a complete list of each of the tools that are being used, so this way that the machinist can double check what they're actually using, what they're equipping into each of the turrets of the machine. Fantastic. And then it goes on a summary of each of the operations, so feeds and speeds for each of the operations, and that's what they need to get the machine set up. The other thing that they need is the actual machine code. So what we've produced so far are all of the tool paths that the selected tools have to follow, but that's not good enough. The machine has to be able to read these toolpaths in a language it understands, and some of the machines are quite old, they all have different languages. So what we do is we feed these toolpaths into something called a post-processor, which grabs the toolpath and converts it into a language that the machine understands. Now these two post-processors are written according to your machine, but there's lots written in Inventor CAM that are there by default that you can tweak for your machines. So we'll have a quick look at that. We'll come to post-process. And here we can choose what machine we're using. So just for this exercise, we're going to be using a FANUC. And then we can say post it out. And we'll say, there we go, sudo projects. Save it as 1001.nc. And this is the machine language that your CNC machine reads when cutting out your operations. Now, as you can tell, it's very, very long and very, very complicated, lots and lots of points. All of these depend on what kind of post-processor you use. Maybe one post-processor might say, hey, go from this point to that point, or define this arc, in which case it will just take one line. Well, there's another one might say, go from this point to 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 this point, and that will be maybe 30 lines long, and that will approximate an arc. It really depends on how the post-processor works, but very powerful. So the last thing that I'd like to point out is that if you make any geometric changes to your model, so say for example, if we were to come to here and we were to make a change, and we'd say, okay, let's go ahead and thicken the midpoint. Oops. Thicken the midpoint so that the geometry changes so that that component's bigger. We don't have to reprogram everything, I'm very, very glad to say. We can just pick the operations and we can click generate, and it will go off and regenerate it for us. And it absolutely saves it if you have to rework any of the designs. So that's the 2D milling operations. Now there's plenty more that Inventor CAM can do, including turning operations, so it's things on a lathe. So if you have a quick look here, if you're cutting something that's turned on a lathe, it can do the finishing operations there. And it can also do some 3-axis simultaneous and 5-axis paths. So say for example, if you've got swaths or curved surfaces, which it has to keep the tool normal to the surface to. Those actually paradoxically are somewhat easier to program than the things that we looked at today. But as you can see, what we can do is go straight from the model to the manufacturing process, and not only assess the manufacturability of it, but also prepare it for the actual machining itself. So this is really the end point of Autodesk digital prototyping, digital manufacturing paradigm. Basically going from designing the model, analyzing the model, finalizing it, and then machining. So thank you very much for your time, and I'll hand you back. Cheers.
Thank you, Frankie. So you've made it to the end of the day. Stay with us for another 5 or 10 minutes. Simon's just going to close the session off with everyone today, and there's a chat box in the window. Please feel free to put any questions that you might have in there. If you might be watching this back on YouTube or anywhere else that we're able to post it at a later date, then there'll be emails lying around. Feel free to comment. We'll make sure that they're constantly monitored, and we'll get back to you as and when we can. Alternatively, pick up the phone. We're always around to help. I'll leave you with Simon.